Assalamualaikum warahmatullahi wabarakatuh. Okay, now we will learn on the molecular structure. Okay, so basically you have four types of energy, okay, which is electronic energy, translational energy, rotational energy, and vibrational energy. So in this chapter, okay, you have to know only two kind of energy, which is rotational energy and vibrational energy. Okay, so the electronic energy is very complex, okay, because it involves the interaction of many charged particles, and the translational energy is not important in interpreting molecular spectra since it's not related to internal structure. So in these topics, we will focusing on rotational energy and vibrational energy. But before that, you have to review back your previous topics in semester 1. Okay, if I'm not mistaken, you have studied on the center of gravity. Okay, you have two atom. Okay, here you have two atom here, M1, M2, and then you have to find the center of gravity. Okay, so here we are focusing on the molecule. Okay, basically on the molecule. Okay, and then okay, so this one is the additional slide that I gave to you, so you may refer this one. This one is you have to review back the relationship between the angular momentum, okay, and what we call the linear momentum, the relationship between those two. Okay, so the angular momentum is given by symbol of L. L is equal to m mass, v is the velocity, r is the radius, sine theta. So because v and r is 90 degree each other, so sine 90 is equal to 1. So you get the overall equation is L is equal to mv times r. Okay, this relation you can see is L is equal to r times p, which p is equal to mv, okay, mass time velocity. So this relation r, the direction is given by the right hand rule. If you are using your right hand rule, you can get the value of the direction of L is actually out of the diagram. Okay, if this one r is here, okay, p is here. If you use your right hand rule right now, the direction of L is outside of the diagram, okay, outside of this slide, okay, basically. Okay, so this one you have to review back. Okay, so this one also a slide for you to review back. Okay, on the existing slide that I gave to you before, there is I think I don't give this slide, but you may refer back. Okay, so you in this topic, the angular momentum, the L is equal to moment of inertia times angular velocity, okay, I times omega. Okay, you can see here, okay, so the rotation is there, this is the radius. Okay, so your L direction will be up if you are using your right hand rule here. Okay, this one is the direction of the angular momentum, L. Okay, so next, okay, this one is the relationship between the angular and linear momentum. So this one is the angular momentum, which is L is equal to moment of inertia times angular velocity. The linear momentum P is equal to mass times V. Okay, so where the moment inertia here is equal to, okay, so this one you have to really remember and you have to study back if you have already forgot what you've learned in previous semester. So you better study this back. Okay, so I is equal to the summation of mass times r squared. Okay, so this one is the moment of inertia for one body or one object. Okay, this one is referred to one object. Okay, so for example, this one, the previous, okay, so I is equal to mass here times radius here, m1 times r1. Okay, this one, so squared here, please don't forget this one. Okay, so next, okay, this one I already copy the figure. Okay, so you can see it more clearly. Okay, if you can see here is m1, m2, so radius 1 from the center of gravity. Okay, for mass 1, this one, r2 for m2. Okay, so you have already known the formula for the relationship between the angular and the linear velocity. v1 is equal to omega r1. Okay, for first body. The second body is v2 is equal to omega r2. Okay, so r1 r2 is the distance. Okay, so the angular momentum is equal to m1 v1 this one previously. Okay, L, so just this one you just include in the formula. So L is equal to m1 v1 r1 plus m2 v2 r2. Okay, so you can take out m1 here, so you can see here m1 r1. Okay, this one from this relation here you can see is v1 is equal to here v1, just substitute here v1 is equal to omega r1, so you will get m1 v1 r1 squared. Okay, this one v1, just you substitute here. Okay, you will get L is equal to m1, okay, omega r squared. So you can take out the omega out. Okay, this one also the same, m2 omega r squared. So v2 is equal to, here you substitute v2, this one v2 is equal to omega r2. So here m2 omega r2 times r2 is r2 squared. So you get here m1 r1 squared, m2 r2 squared. So the omega you can take out here. Okay, and then you can simplify this equation. So m1 r1 2 plus m2 r2 squared is equal to the value of I, this one, previous formula. Okay, the summation, okay, I is equal to the summation of mass of the body times r squared of the body. So the summation okay, so the summation of body number 1 and body number 2. Okay, so you get L is actually is equal to I omega. Okay, that one is the first formula. The second formula is the rotational energy. Okay, this one is related to the kinetic energy. So it's equal to half m1 v1 squared plus half m2 v2 squared. So you can simplify both of the equation. Same, you just substitute here. So you can get E rotational is equal to half I omega squared. Okay, by solving this equation 1 and 2, you will get the formula of E rotational is equal to L squared divided by 2I. Okay. Okay. Okay, next, okay, this one is the reduced mass. Okay, reduced mass formula. So I is actually equal to mu times r squared, where r is the radius between the two body, this one R. Okay, the total radius between two body, between M1 and M2. Okay, so please focus on this term, reduced mass. Okay, because the question will ask you to calculate the energy, but before you want to determine the value of energy, the first thing that you have to do, or actually have to do, is to find the reduced mass of the molecule. Okay, unless you cannot get the answer. Okay, so mu is equal to M1 times M2 divided by M1 plus M2. Okay, this one, mu is equal to this one. Okay, so R squared, this one is the value of the distance between the two bodies, between M1 and M2. Okay, between M1 and M2. Okay. Okay, angular momentum L is always quantized in nature. Okay, the quantization rule is equal to this one, L is the energy level. Okay, you can see here the energy level between 0 to 6 here. So this value will depends on the question. Okay, so they will ask you the energy between the level. Okay, so it depends. So you can I will show you in the question, in the example question. Okay, so here the allowed energy for rotation is, okay, E rotational is equal to H bar squared times L bracket L plus 1 close bracket divided by 2I. Okay. Okay, cm here is the meaning is a central mass, central mass. Okay, so you have to remember this equation. Okay, I will show you how to use this equation. Okay, but first you have to remember this one, the H constant. You can find the value in at using your calculator, but be careful. This is the Planck constant, but the Planck constant have two value which is different. This one is H bar, another one H without bar. You can see this bar here. Okay, H with a bar. Okay, and another one is H without a bar. Both of them are Planck constant, but the value is different. You can check using your calculator. Okay, this one is non-formula. Okay, this one. Okay, before that, okay, so this one is the formula, the same formula as this one, but this one, this equation is for if the question asks you the different level of quantum energy level, so you have to determine the exact formula that you have to use. Okay, you just substitute the value of the level asked by the question, so you just you can directly get the answer from the substitution. Okay, okay, and this one, omega is equal to energy, okay, difference of energy, this one divided by H bar. Okay, this one is the loss and gain photon emission absorption at certain frequency. Okay, certain frequency. Okay, okay, I will show the detail on the example. Okay, let's say, okay, let's go for the example. Okay, example number 1. Okay, you can see this question if you have this book. Example page 281. Okay, okay, let's see the question. The carbon monoxide CO molecule has a bond length R of 0.113 nanometer, and the masses of the carbon and oxygen atom are respectively 1.99 times 10 power of negative 26 kilogram, and 2.66 times 10 power of negative 26 kilogram. Okay, so find the energy. Okay, the first question, find the energy, and the second one, the angular velocity. Okay, the angular velocity, which is omega. So you have to be very familiar with the term and the symbol to make you easily to predict the formula, which formula that you have to use. Okay, the angular velocity, which is omega, of the CO molecule when it is in its lowest rotational state. So I will explain when it is at the lowest rotational state. Okay, now for the first question, okay, you just take out whatever information that the question give to you. Okay, R, the value of R is equal to 0.113 nanometer. And then for carbon, the mass of carbon here, oxygen, here is the value. Okay, first what you have to do is you want to find the value of energy. So before that, you have to calculate the reduced mass, which is the value of mu. So from previous equation, you have know the reduced mass formula is mass 1 times mass 2 divided by m1 plus m2. So the value is 1.99 times 2.66 divided by total number of the two atoms. This one. So this one is the same, so you can put the value at the back here. So you get the reduced mass is 1.14 times 10 power of negative 26 kilogram. Okay, after you get this, you have to calculate the moment of inertia. Okay, so here I is equal to mu times r squared. Okay, this one is given. Okay, this one you have already calculated before, this one. So just substitute in the equation. Okay, mu here, this one. So this one is the value of R. Okay, so you get the moment of inertia is 1.46 times 10 power of negative 46 kilogram meter squared. Okay, now the question asks you find the energy. If the question does not mention what level of energy, so we assume the lowest energy is when L is equal to 1. So we just substitute the value of 1 into this equation. Okay, 1 here, 1 here. So you simplify, you get h bar squared over I. So you just substitute this one, you can just use your calculator. You can find the value of h bar is equal to 1.054 times 10 power of negative 34 joule second divided by 1.46 times 10 power of negative 46 kilogram meter squared. So you can get your energy in joule. Okay, so the value here is 7.61 times 10 power of negative 23 joule. Okay, so you can leave your answer in joule, or you can convert to electron volt. You can use the constant 1.6 times 10 power of negative 19 to convert from joule to electron volt. But both answer is acceptable. Okay, you can answer either one. Okay. Okay, next, okay, the angular velocity, which is omega. So this one from previous equation. Okay, E is equal to half I omega squared. So you want to find the angular velocity, which is omega. Okay, so omega is equal to sec over 2E over sec I. So you just substitute into the equation, so you can simply get directly answer. So you must be careful with the unit. So you have to remember your angular velocity is equal radian per second, the unit. So all of your answer must have the value and the units, okay, to get a full mark. Okay, this is compulsory. Okay, and then we go for next. Okay, this one is okay. Okay, go for another example. Okay. Okay, in carbon monoxide also. Okay, this one you can try. Okay, so it give a different energy from 0 to 1. Okay, absorption line occurs at frequency K. So in this question, it give the value of frequency, okay, in hertz. What is the bond length of CO molecule? Okay, so here I give you the answer. So you just determine how to get this. Okay, you can try to do first, and you can if you cannot get the answer, you can ask me. Okay, so here is some of the sample of the past year question. Okay, let's see the first question. Okay, electromagnetic radiation illuminates a crystal germanium. Okay, calculate wavelength photo emission generated by this interaction. Germanium is an elemental semiconductor with a band gap of 0.7 electron volt. Okay, simple question. Okay, there is only one information here. Okay, so the question asks you to calculate the wavelength. Wavelength is lambda. So when you got the question, you have to determine what is the parameter that have been asked by the question, okay, before you answer. So here you have to find the value of lambda. So the relationship between the band gap and lambda is equal to E, okay, E is equal to HF. F is the frequency, where F is equal to C over lambda. So you want to find the value of lambda here. So lambda, actually you can skip this step. Actually you can just use directly lambda is equal to HC over band gap over E. HC over E, lambda you can bring to the left. So here lambda is equal to, okay, Planck constant. Okay, so this one you can see the H, the Planck constant without bar. So here the value of H here is 6.63 times 10 power of negative 34 joule second. So please make sure the value, which formula using which H. Okay, H and H bar is different. Okay, so both have a different value. So make sure you are not substituting the wrong value. Okay, C is the speed of light, which is constant. Okay, this one I think you have already known. Okay, 3 times 10 power of 8 meter per second. Okay, so this one is just substitute the value of band gap here. So this one you have to times constant here, because you have to cancel this one, your unit here, electron volt. Okay, electron volt here and here. Okay, so you substitute, so you will get your answer is in 1.78 micrometer, or you can leave your answer 1.7x times 10 power of negative 6 meter. So I don't want. Okay, and then we go for the second example. Okay, the atmosphere is made up of 79% of nitrogen gas, okay, N2 gas, and then 20% of oxygen gas. Okay, consider an oxygen molecule with their atomic mass of 16U. Calculate. Okay, first the reduced mass. Okay, this one is direct question. It asks you to answer the reduced mass of oxygen molecule. Okay, you can see the trick here is sometimes the question give you a lot of information, but it just asks you to calculate or focus on only one molecule. So in this question is oxygen. Okay, nitrogen, the question does not focus on the nitrogen gas at all. Okay, you can see here all the question is focusing on the oxygen. So this one is just added or just to make up the question. So don't be afraid, just focus on the question, the main question. Okay, so this one is direct. Okay, so the reduced mass, so you know the reduced mass mu is equal to m not, this one is not m not, this one is m o. I using o here. So because oxygen gas have two atom of oxygen, so you have to use two kind of symbol lah, MO. So 16 times 16, so given the atomic mass here is 16U. Okay, so 16 times 16 divided by 16 plus 16, so you get here 16 over 2. So you simplify times one, this one you have to convert to kilogram, so this one is in U unit, okay, which is atomic mass unit. So you have to times 1.66 times 10 power of negative 27. This one is kilogram, actually kilogram. Okay, so you will get your answer is 1.328 times 10 power of negative 26 kilogram. Okay, so your first question is solved. And then the second one is the characteristic rotational energy for the oxygen molecule. Again, the oxygen molecule whose bond length is 0.121 nanometer. So you can see here. Okay, so here some of the tips. Okay, so this one, this term, so you have to be careful on these terms. The characteristic rotational energy. Okay, characteristic. So if the question asks you to find the characteristic rotational energy, so the equation is this one, E O R. This one rotation for rotational at E O R at origin is equal to H bar squared divided by 2I. Okay, this one characteristic rotational energy only for this one. Okay, so just substitute directly into the equation. So H bar you have already known, the value is 1.054 times 10 power of negative 34. So divide by 2I. I here is equal to, in previous slide you have already known, the moment inertia. I is equal to mass times radius squared. Okay, so the mass here you have already calculated before here. So this one is the radius between the bond length between the oxygen, okay, between the oxygen atom, okay, atom from one atom to another atom. Okay, so both are molecular, so between atom and atom is 0.121 nanometer. So squared, don't forget this one, squared. Okay, you will lose mark here if you forget. Okay, so don't miss the step. So here your answer will be in joule or electron volt. You can give either one. Okay, but if the question asks you to answer in electron volt, then you have to convert into electron volt. But if there is no request from the question for you to answer in joule or electron volt, so you can answer in both. Okay, it doesn't matter, so both answer are acceptable. Okay, and the next one is on the energy photon. Okay, you have to calculate the energy photon emitted in. Okay, so now, okay, you can see here, now the question is ask you to calculate the energy from level 2 to level 1. Okay, so now we are using this equation. Okay, So this equation, so this one, because this one is a constant, so you can put aside first. Okay, so this one, the first, the final, you have to divide, you have to minus with the initial. Okay, here from 2 to 1, so from level 2 minus level 1. So this one you put aside. Okay, so this one you substitute the value 2, 2. Okay, this one is constant, so minus L1, the value is 1, L1 1, so this one constant. So you get this final equation. So you just substitute the value of h bar here. Okay, squared, don't forget this one. So divide by 2i. Okay, so you get the answer in 7.16 times 10 power of negative 4 electron volt. Okay, so this value you can get direct from here, right? So this one 1.76, this one is in electron volt. You can also answer in joule. Okay, 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 that one is for rotational. Okay,